In this video, we'll be talking about the superposition of electrostatic forces, and we will be dealing with systems that are linear or in one dimension. When we talk about the superposition of electric forces, then we're talking about the total overall, the overall or the resultant force. The resultant electric force is the vector sum of the electric forces between the individual charges. So we have to check how many forces we have and find their resultant as a vector sum. If they are linear, we deal with them in a certain way. If they were in two dimensions, we will deal in another way, and we will see this in another video. Let's take an example. Find the net electric force acting on QC. We have three charges, QA, QB, and QC. We have to know the net electric force or the resultant force acting on QC. So we have the force by A on C and the force by B on C. How do we solve for this? First, we have to draw the forces. I will hide QB. I will assume I only have two charges, which are QA and QC. Since we are finding the net electric force acting on QC, then we have to draw all the forces that act on QC, not the forces applied by QC on other objects, all the forces applied on QC. So I will think this way. A is negative, C is negative. They are like charges, so they will repel. What would be the effect of A on C? I will say A will repel C in this direction. So the force applied by A on C is in this direction, FAC. Now I'm done with A and C, but I still have B, so I will hide QA. Now, QB and QC are both negative. They are like charges, so they repel again. Then I'm studying the effect on QC, so I will say QB will repel QC away. It will push it away, so in this direction to the right. So this will be FBC. I'm done drawing the force vectors. Now I have to start the calculation. FAC is equal to KC QA QC over RAC squared. QA is given as negative 2 microcoulombs. QC is negative 1 microcoulomb. And the distance between A and C is this distance. So it is 3 plus 5. So for KC we replaced 9 times 10 to the power of 9. QA is negative 2 times 10 to the power of negative 6. QC is negative 1. Again, we convert from microcoulombs to coulombs times 10 to the power of negative 6 over R to the power of 2 or R squared. The distance from A to C is 3 plus 5, which is 8 meters squared, and we get this answer. Next step is to calculate the other force, which is FBC. FBC is equal to KC, QB, QC over RBC squared. So KC is 9 10 to the power of 9. QB is given as negative 5 microcoulomb, so negative 5 times 10 to the power of negative 6. And QC is negative 1 microcoulomb, so negative 1 times 10 to the power of negative 6. The distance from B to C is 5 meters, so 5 squared. And the final answer for FBC is 1.8 times 10 to the power of negative 3 newtons. Now we're done calculating FAC and FBC. I have to calculate F net. To calculate F net, I have to look at the force vectors. They are both pointing in the same direction towards the right. So the net is their sum this way. F net is equal to FAC plus FBC. So we replace and we get the answer as 2.08125 times 10 to the power negative 3 newtons, and the direction is to the right because they are both going to the right. We will follow the same strategy in this example. We have three charges, QA, QB, and QC. We have to find the net electric force acting on QC. So first I will consider that I only have A and C, and then I will consider only B and C. I will separate them. So I hide QB. Now we have QA and QC. QA and QC are both positive. They are like charges, so they repel. They push each other away. So the effect of A on C is that A will push C away in this direction. Then we hide QA. QB and QC are unlike charges, negative and positive. So they will attract or they will pull each other, and B will pull C or attract C this way to the left. So this is FBC. Now we calculate FAC. KC is 9 times 10 to the power of 9. QA is 6 times 10 to the power of negative 9, converted from nanocoulombs to coulombs. And QC is 3 nanocoulombs, 3 times 10 to the power of negative 9. The distance from A to C is 3 meters plus 5 meters, so 8 meters squared. And we get the answer as 2.53 times 10 to the power of negative 9 newtons. For FBC, we apply the formula of Coulomb's law, Kc QB QC over the distance from B to C squared. Kc is 9 times 10 to the power of 9. QB is negative 5 times 10 to the power of negative 9. We converted from nanocoulombs to coulombs. And QC is 3 times 10 to the power of negative 9. The distance from QB to QC is 5 meters, so 5 squared. And we get the answer as 5.4 times 10 to the power of negative 9 newtons. Now we have to find Fnet. We look at the force vectors. FAC is going this way and FBC is going opposite to it. So Fnet will be FAC minus FBC, or if we want to take it as a vector sum, it will be FAC plus minus FBC. We will get the same exact result. So Fnet is FAC minus FBC in an absolute value. We replace to get the answer 2.53 times 10 to the power of negative 9 minus 5.4 10 to the power of negative 9. We get this answer. Now, how did we know that the direction is to the left? When we have forces in opposite directions, the greater vector or the vector with greater magnitude decides the direction. We have 2.53 10 to the power of negative 9, 5.4 10 to the power of negative 9. So FBC is greater than FAC, and FBC is pointing to the left. So the direction of the net force is to the left. Example 3. The same concept, the same strategy. We have 3 charges. We have to find the net electric force on QC. So we hide B. A will repel C away. Then we hide A. B will repel C away. They are both in the same direction in this case. We calculate FAC. We replace to get the answer. We calculate FBC. We also replace to get the answer. And then to find Fnet, since the two vectors are pointing in the same direction, then Fnet is the sum. We add them to get the net force or the resultant force. So Fnet is equal to FAC plus FBC. We add them to get this answer. The direction is to the right since they are both pointing to the right. Same concept. We hide QB. QA attracts QC, so FAC should be to the left as we see. Then we hide A. QB will attract QC to the left as well. So now we have two vectors pointing to the left. To calculate FAC, we replace in Coulomb's law. 9 10 to the power of negative 3 for A. We convert from millicoulombs to coulombs. Negative 5 times 10 to the negative 3 for QC. We also convert. The distance from A to C is 3 meters plus 7 meters, so 10 squared, we get this answer 4050 newtons. And then we calculate FBC, which is KC QB QC over RBC squared. Again, we replace KC with its value. QB is 5 times 10 to the power negative 3. QC is negative 5 10 to the power negative 3 over the distance from B to C is 7 meters. So over 7 squared, we get 918.37 newtons. Now for F net, okay, we have nothing on this side. So on this side, it is 0 minus this side. So this is how we do it. F net is equal to 0 on the right side minus, on the left side we have FAC and FBC. So minus FAC and FBC, and we get this answer. The direction is to the left since both vectors are pointing to the left. Find the net electric force acting on QB. We hide QC. A will attract B, so FAB will be pointing this way, to the left. Then we hide A. C will be attracting B, so FCB should be pointing this way, to the right. Then we calculate each force. FAB is equal to KCQAQB over RAB squared. We replace the values. Do not forget to convert. The given charges are in nanocoulombs, so you multiply by 10 to the power negative 9 as you see. The distance from A to B is 3 meters, so 3 squared, and we get the answer as 1 times 10 to the power of negative 8. Then FCB, KCQCQB over RCB squared. We replace. KC is 9 times 10 to the power of 9. QC is negative 4 10 to the power of negative 9, and the QB is 5 times 10 to the power of negative 9. The distance from B to C is 5 meters, so over 5 squared, and we get this answer. Now for F net, it will be the right side minus the left side, so FCB minus FAB as a magnitude. And we get this answer. Y to the left, let's check. FAB is 1 times 10 to the power of negative 8, and it's pointing to the left. FCB is 7.2 times 10 to the power of negative 9. 10 to the power of negative 9 is less than 10 to the power of negative 8. So this is the force with a greater magnitude. It's pointing to the left, so the net force will be to the left. Another example. Find the net electric force acting on QB. We hide the QC, we draw FAB. Then we hide the QA, we draw FCB. Then we calculate each force. FAB is equal to KCQAQB over RAB squared. We replace the values of KC, QA, and QB over the distance between them, which is 3 meters squared. We get the answer. Then for FCB, KC, QC, QB over RCB squared. We replace the values for KC. QC is 1 nanocoulomb, QB is negative 1 nanocoulomb, and the distance from C to B is 5 meters, so 5 squared. For F net, it will be FCB minus FAB. Now, if we compare FAB to FCB, FAB is 2 times 10 to the power of negative 9. FCB is 3.6 times 10 to the power of negative 10. So FAB is greater than FCB. Before we find F net, we can conclude that the direction of the net force will follow FAB, which is to the left. Why? Because again, its magnitude is greater than the magnitude of FCB. So to find F net is equal to FCB minus FAB in an absolute value. We get the answer, and the direction will be to the left. A third example, find the net electric force on QA. So once we will find the force by B on A and then the force by C on A. First, I will hide QC. So we have to draw the force by B on A. B is negative, A is positive. They are opposite polarities. They attract. So B will pull A. Why? Because we're finding the force on A, so we draw the forces on A, acting on A. So this will be FBA, it will be attracted towards B. Then we hide B and we draw the force by C on A. Again, they are opposite polarities, so they attract. So the force by C on A goes also to the right. We calculate the forces. FCA is QC, QA over RCA squared. KC is a constant. QC is negative 3 nanocoulombs, we convert it. QA is 2 times 10 to the power of negative 9 converted over the distance from C to A is 5 meters plus 3 meters, so 8 meters squared. We get the answer in newtons. Now we find FBA, KC, QB, QA over the distance from B to A squared. We replace Kc with its value, Qb converted from nanocoulombs to coulombs. Same thing for Qa over the distance from B to A, which is 3 meters squared. We get the answer. And then to find Fnet, since they are both in the same direction pointing right, then Fnet is equal to Fca plus Fba. We replace and we find the answer. Now find the net electric force acting on QB. So we have to find the force by A on B, the force by C on B. First, let's hide QC. After we hide the QC, we draw the force by A on B. They are like its charges. They repel. They push away from each other. So A will push B away this way. This is the force by A on B. Then we unhide C and we hide QA. C and B are unlike its charges, so they attract. So C will attract B, so F of C on B will be also to the right. We calculate FAB, KCQAQB over the distance between them squared. The conversion now is from microcoulombs to coulombs, so times 10 to the power of negative 6. We replace QA, we replace QB, the distance between them is 3 meters squared. We find the answer. Then FCB is KCQCQB over the distance between C and B squared. KC we replace it. QC is negative 1 microcoulombs. We convert it negative 1 times 10 to the power of negative 6. QB is 5 times 10 to the power of negative 6, and the distance between them is 5 meters squared. We find the answer. Now, since they are both pointing the same way, then Fnet is equal to FAB plus FCB, and the direction is to the right. Find the net electric force acting on QB. So FAB and FCB. We hide QC first. The force of A on B, they are unlike charges, so A will attract B this way. Then we unhide QC and we hide QA. C and B are unlike charges, so they repel, so C will repel B this way to the left. Then we calculate each of the forces. FAB is KCQAQB over the distance squared. QA 2 10 to the power of negative 6, QB negative 5 10 to the power of negative 6 over 3 squared. We find the answer. Then we do the same thing for FCB and we replace to get the answer. Now for Fnet we have nothing on this side, so 0 minus this side, so it will be like this. 0 minus FAB plus FCB, we replace 0 minus FAB is 0.01, FCB is this value, and we get this answer, and it is to the left since both forces or force vectors are pointing to the left. Find the net electric force acting on QC. Now, we hide QB. A and C are unlike charges, so A will attract C this way, FAC. Then we unhide B and we hide QA. B and C are like charges, so B will repel C away. So this is FBC. Then we calculate FAC. We replace the values. We find the answer. Then FBC, we replace the values and we also find the answer. Now, the net force, since they are in opposite directions, will be FBC minus FAC in the absolute value. Even if you put FAC minus FBC, since we are using the absolute value, we'll get the same answer. You only have to detect the direction. So FBC minus FAC, I replaced the answer and I got this number. This is the magnitude of the net force. The direction is to the right. Why to the right? If you compare the values, this is FAC, which is 5.625, 10 to the power of negative 4 newtons. FBC is 1.8 times 10 to the power of negative 3 newtons. So the FBC is greater than the net force follows the direction of FBC, and FBC is pointing right, so the direction is to the right.